Okay, welcome everyone. Today we are streaming. Today is what? It's Saturday, right? We're at Microsoft Office, and unfortunately today we're not streaming from the terrace because it's cold and it can start raining any single moment. So I had to be here inside so we can stream without disruptions. Yeah, because previous time I think I tried to switch from the corporate Wi-Fi to my hotspot, and OBS straight away just dropped everything. So yeah, I'm not gonna do it again. So yeah, so about maybe any updates or something like that, we keep going with our LeetCode 75. Currently, for those who are interested, we're just solving LeetCode problems, trying to catch up with our skills that I kind of lost 3 years ago after I joined Microsoft. So yeah, I need to catch up with this and improve my skills to the same level as it was before I joined, right? So in case any layoffs, anything like that, we are ready, right? Yeah, that's basically the idea. So we are moving slightly, and previous stream and this stream they will be about dynamic programming. So previous stream what we have solved basically is one-dimensional DP problems. For example, yeah, all of them. We went quite good. So the rule and the goal for that is to try to learn how to do a proper recursion, then how to change it to top down, and then the key transition is to convert basically the top down memorization to bottom up, which is not that hard, and usually you can do it even by formal number of steps without thinking too hard. And this is what we're gonna do today. So today we are going to solve maybe these 2 questions, and also let's maybe review. One disclaimer: please don't forget to subscribe to my Telegram and Instagram, because this is the place where all the updates are happening, right? So one of the updates was about the Lit rooms. So me and my friends, we are kind of preparing together and catching up on interview skills together. And the thing is that, yeah, we were doing Lit rooms, which is basically the browser extension when you can create the web room in a sense, add the people there, and then basically you can solve LeetCode problems in a competitive way. So these are the problems that we were solving before. Yeah, so we're gonna basically review them, maybe one by one. Just quick one to recap the patterns we learned so far. What's up, Mr. Andrej 27C? Nice that you help people work to these problems. Yeah, thank you. Yeah, I also mainly helping myself, right? So average of levels in binary tree, 637. LeetCode. Let's go. So this is the question. It's basically easy. So again, the root binary tree, return the average value of the nodes on each level in the form of an array. So this is level 1, this is level 2, this is level 3, and so on. So usually and typically when you need to do something level by level in binary tree, you are using BFS, which is breadth first search. How this exactly works? First of all, breadth first search is cool because it's iterative, so you will not be dealing with converting recursion to the iterative approach in your follow-up, right? So you don't need to waste your time on it. And basically the algo would be that you're starting your queue from this guy, from the root, right? Then you explore these two guys and you put it into the queues, right? And you traverse level by level and by size of your current queue. So initially your queue would have only 3. Then after traversing this guy, the average sum would be 3 for it because it's 3 divided by 1, right? Then you explore these two guys, your queue is going to be 920. Actually, there is no big difference in order in which you're gonna to process this item. So you basically process this one and you're gonna have for loop consisting on only 2 iterations here. So it's gonna be 9 plus 20, 9 plus 20, 29, and it's divided by 2. So this is your average, and basically you're done because you popped these 2 elements. Let's say this element gonna have, I don't know, someone here, and then you do exactly the same. So while you're traversing this one, you put this one in the queue and these 2 in the queue, and then you'll have queue of size 3. You're gonna compute average based on queue, and this is basically breadth first search level based traversal of binary tree or any kind of tree, basically. As easy as that. You don't need to memo anything because you're not gonna process something twice, and the time complexity is basically O of n, where n is basically number of all elements in the tree, and memory is basically the level size, which in worst case, if the tree is full, it can be pretty much close to n as far as I remember, so it's pretty much O of n. Yep, so pretty much easy problem. What next do we have? Array partition 561. So 561 array partition. This one was a bit tricky because for a bunch of reasons. It's not that easy to come up with the greedy approach, right? So given an integer array nums, group these integers into n pairs such that sum of minimum of both of elements in the pair is maximized. So order doesn't matter, nothing is matter. You can use the element only once. So in this case, you see that you can choose 2 pairs out of 4 items. Like you cannot choose more, right? And you need to maximize the sum of minimums of these 2 items. So you clearly can see that you want to have the biggest value in your pair because that's how your sum will be maximized, right? So in the end, it turned out after this example that I draw right here, that sorting will help because the greedy approach would be to actually get you anyway need to form all the pairs, right? And the best way to form the pairs is to basically group as close as high number values as possible, and this can be done only by sorting. So you sort and you just take them, and that's it. And then take pair by 2 and yeah, return the sum. Pretty much easy, but it was not so naive approach and not so intuitive for me. I have to be kind of honest with you, but I felt pressure on competitiveness, so I just like, it was my guess, maybe by sorting it can be maximized. I tried, coded it in, I don't know, in 20 seconds, and it was actually the right approach. So 2216 LeetCode. Minimum deletions to make array beautiful. Oh, I love these problems about the beautiful arrays, beautiful shit, and yeah. So basically, what should be done here? This thing has a bunch of solutions again, I guess. So we have array of nums, and what should we ensure, or not ensure? What should we do is to make this array beautiful. An array is considered beautiful only in case if the length is even. This one is easy, so just length mod 2 equals 0, pretty easy. But also, what should we ensure that nums under index I is not equal to nums to the next basically number. And this one is a bit tricky because we can delete any number of elements from nums. When you delete an element, all the elements to the right of the deleted element will be shifted 1 unit to the left to fill the gap. Yeah, so basically, naturally, what I started thinking is about using stack or something like that. So we need to return minimum number of elements to delete to make it beautiful. So pretty much, let me put this one up here. So yeah, don't forget to subscribe. Telegram is very important, very important. Yeah, what I wanted to show you, yes. So is this example how it can be solved. So what we want to ensure basically is that these two, they are not equal, and then these two, they are not equal, and this is actually correct. And 5 is like, it doesn't have pair, right? Let's not confuse this case when they can overlap. They cannot overlap in this example. So what we want to ensure is that these kind of 3 segments, they have not equal nums. So basically, the way I would do that usually is just have some kind of stack or whatever. So I have 1, this is my stack. And I'm just iterating over the numbers, and I see, okay, this is 1, right? We already have 1 in the stack, so it cannot be beautiful array. So we just basically skip it. We increase some count. We make it equal to 1. We skip this number. We we meet this number 2. And since this is like complete the segment and we are done with that, we can basically drop our stack completely and proceed with 3 and 5. Because as I told you before, the segments are not overlapping. So it's not like this. It's not like this. But even if it would be like this, the stack is still the solution that will work. So basically, this was the solution. And then the only thing, like after this for loop, we kind of sure that the pairs, they are not. So nums under index I is not equal to nums under index I plus 1. So this clause is basically going to be correct. But let me also show you what will happen in this case. So let's say we have our stack right here. We start with number 1, right? Also, so you can see the solution exactly. So we start with number 1. Now we see this number, it's 1. We skip it. We increase our count. Now we and this number, it's 2. Good. We are done. Remove from stack completely. Create new stack. Now we are with this number, it's 2. And this number is 3. So we have our pair. We remove the stack. It's good. Now we have the last number 3, and that's it. We are done. So as you can see, we only need to do 1 removal of the character, but the resulting array would be 1, 2, 2, 3, 3, which is length of 5, which makes this array is not even. which makes this array not beautiful. So for this reason, we are adding just +1 operation because, yeah, we're just removing any number, and this will make this array beautiful, basically as simple as that. And then the last thing that we had here, max area of island, 695. So LeetCode 695. Max area of island. This is actually a very good problem. I love the problems that are related to graph. You have some feeling that you're, working with something real. Don't know how to explain it. So basically you're given the grid, blah blah. Island is basically marked as ones. You can move 4 directions as always. The area is a number of cells with value 1 in the island. So basically these are islands, and the biggest one or maximum area is this one because it has 1, 2, 3, 4, 5, 6 elements, and all of these guys have less than 6 elements. So we gotta return, yeah, the length or the size of this island. So basically you're doing DFS. DFS is the native approach to this problem, I would say. So you basically traverse all the matrix, right? This is happening here, and if you meet not 0, so 1 here or here or here, whenever, you just start doing your DFS algo, which starts exploring to all the directions and keep counting how many cells you have visited. And when you visited it, you can use a specific set to keep the visited values, so you don't go with the Stack Overflow to not visit it again, or you can modify the array straight away. So let's say we are starting here at this point, so I'm visiting 1, so I'm counting this as 0, and yeah, my count will be 1, so it's already 1 plus. I have 4 directions to move, basically here, 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 and here, and only one valid direction can be possible because these are zeros, we don't care, and this is 1, so we move here. We also set it 0, so we cannot move upstairs, for example, because we already marked it as 0, we don't care. We add in +1 at this point as well, then only also one valid position here, we again set in 0, again adding +1, and again same happens here. Then we return it all the way back in our recursive function, and then basically the result, we keep maximizing the result all the time, and that's how you proceed. Basic DFS, but yeah, you should always be ready to do your DFS whenever it is required, right? All good, all good. These were the Litroom's problems. Now let's get back to our dynamic programming. So previous time we were solving one-dimensional dynamic programming problems, or category, I don't know how to name it. And with 1DP, it's clear that with one-dimensional dynamic programming problem, you're gonna have only one dimension of sub-problems or cached values or whatever. So basically, the algorithm is usually the following: you create recursive solution for sub-problem whatever x, sub-problem I, whatever. So the property of this recursive function, this function actually should accept the input as a sub-problem, and it should return the value as answer to the sub-problem. This is very important because there were a lot of time, let me do this, I guess, yeah, so you can see it well. There were a lot of times when basically I was calling up the recursion for the dynamic programming, and I was putting my output or some weird values into my parameters into the function, and it led basically to the dead end situation, because you cannot memorize dynamic programming problem that does not have the input parameters that are only related to sub problems and nothing else. Then step 2 would be add cache on top. So this is something that is called top-down dynamic programming solution. You basically add the cache into your dynamic programming recursive solution, and it decreases the complexity from the exponential to polynomial, I guess. This is the mathematical word. And then the third step, as a usual follow-up during the interview, convert to iterative bottom-up. This step is one of the trickiest and one of the hardest during basically your LeetCode practice, and it was the same for me, but you can find actually a few formal rules how to convert your top-down to bottom-up without actually changing much the code and kind of making sure it will still work. Step number 4 would be optimize space. In case of one-dimensional dynamic programming, usually there are cases where you can optimize space to constant from O(n). In case of two-dimensional dynamic programming problems, you usually can decrease space from n squared to n, which is not that big of a deal. Actually, I wouldn't mind if interviewee would push me solution with the bottom up, but without optimizing the space, I would be quite okay with this approach. So yeah, let's basically solve the problem. So this is pretty typical two-dimensional dynamic programming problem. So we have a grid, we have a robot starting at position 0, 0. The robot tries to move bottom right corner. The robot can only move either down or right at any point in time. So basically what is happening here is the following. We have this robot. Where is my guy? Yeah, we have our robot, and it can move either to the right or to the bottom. And that's it. And with this approach, sooner or later, it will reach this finish. Our task is to return the number of possible unique paths that the robot can take to reach the bottom right corner. And okay, so let's analyze this. We are at position here, 0, 0. We can move here and we can move here. How many ways we can move to this place? Only one, because we are starting at this position. This cell is not possible to reach, so only one possible move. So we put in here 1. Same way happens to this guy. But how many ways to get to this cell? So there is basically, we can move like this and we can move like this. So 2 ways to reach to this cell. Let's say we want to reach to this cell. So how many ways we can do it? So we can do like this. We can do like this. We can do, I guess, like this. Is there any other? Yeah, since we cannot move left, we cannot do like this. So it's gonna be 3, I believe. Now, how we can think about this in terms of the dynamic programming? I edit your videos and design with. I edit your videos and design thumbnail. I'm sorry, but what do you mean? What's wrong with my thumbnail? Usually we are actually streaming on the terrace, so the thumbnail is actually it is using the old it's using old part, so it's 27, but actually it states 26. Anyway, I don't think it's that much of a deal. Yeah, so let's think about how we can convert this problem to sub-problems. So again, we can reach this path in 1 step, this path is 1 step, this path in 2 steps, or in 2 ways, sorry. So there is way from here and from here. Now, talking about this one, we can only step here from the top or from the left. And from the left, we can step here only one way of doing that, because we cannot move from left, and we cannot move to the left. And to get to this point, there are 3 ways. So you can basically observe that in reality, the number of... am I interested? No, thank you, I'm not interested. Man, I'm not making money out of YouTube. So, yeah. I'm not that... I would say... I don't worry that much for now about the quality and all this stuff. We're just having fun here. So, we can reach to this place, and you can... what actually you can observe, that for every single step that you want to calculate, let's say this one, we can go here only by going from this way or this way. So basically it means the number of ways to get to current cell is the number of ways to get to the cell upstairs, so from the top, and the number of ways to get to the left, because these are the only direction that you can come from. So 1 plus 3 is going to be, plus 2 is going to be 3. And same thing works everywhere. And in the end, you're gonna observe that actually, this we're gonna discuss when we're gonna go to bottom up. Especially it's good because it's grid, so it's pretty much fits the dynamic programming table. But in a nutshell, how you can calculate your recursive function that you want to get to this place, and your recursive function should tell you how many ways there are that can lead me to some cell under row R and cell C, or column C. So your recursive function gonna calculate you how many ways that there are to reach this finish star. And you start collecting it by observation that, okay, to this star I can reach only by following from this cell or from this cell. And now you're gonna calculate how many ways to reach to this cell and how many ways to reach to this cell. This will spawn you again the recursive calls for these 2 guys. And you can see that you're recalculating this guy twice already. So this is, of course, this already seems like a sub problem. So let's basically solve it pretty quickly. Like that. So let's first define the recursive function. So how many? I would name it how many is the size, or sorry, is the font size okay? I hope so. So how many? And this is for row and column. So definitely what we should do, let's start with the base cases. So our base case, we're gonna call this function later on like this, how many, and the number of rows is, okay, we already have it. So the number of rows is m, am I right? Yes. And number of cells is n. But since these are indices, we're gonna have like this. And this is what we should return. And let's define basically our recursive function, how many for the particular row. So the base case, so how many ways? The base case would be we eventually gonna call sub functions and reach 0, 0. So for 0, 0, there is basically only one way. So if r is equal 0 and c equals 0, we return, we only return 1. Let's think about boundaries a bit later. I see you solved around 400 problems on LeetCode. Yes, I solved 1.2K, but still didn't get placed in big tech. You know why? There are a bunch of reasons. Actually, when I got my first job at Microsoft, I think I sold like 150 or something like that. There are a bunch of reasons. Actually, market right now is not good. I know it by experience and by talking to my friends as well. Right? So market is very bad now. Too many applicants, Too many companies are doing layoffs. Too hard to get through and get any attention. And also, yeah, LeetCode is not only the thing. There is system design, right? There is behavioral, there is experience, there is bachelor. So your CV might get totally ignored just because of it's not good enough for them, right? So a bunch of reasons, but tell me why. I'm interested. What happened? Like 1.5k LeetCode problems. This is a lot. I have to agree. This is a lot. So this would be our base case, and yeah, I guess since we are moving only in this case upwards, because we are starting at star and we are interested what is the value here and what is the value here, we can reach only this, and like what is the out of boundary case in our case. These two cases, right? We don't want to go here. So for that reason, I would state if row is less than 0 or column is less than 0, we return 0, because there is 0 ways to reach there. And now our DP formula, or whatever you call it, it will be, so we want to know how many will be to the row above, so r minus 1 same column, plus how many same row but column minus 1. And this is basically it. This is basically it. I guess at some point we reach here. Yes, it should actually work. Yeah, it works, but let's analyze the complexity, right? So you can clearly see that we are calling two subfunctions at every single function call. So our recursive stack would be that we are starting with, sorry, let me draw somewhere here. So we're starting with m minus 1 and n minus 2. Let's say m and n are 10. So we're starting with 9, 9. Then we are spawning 8, 9, and 9, 8. And these guys are spawning again 7, 9, and 8, 8. And this guy is spawning 8, 8. And oh my god, how 9, 7, yes. And you can see that every single level, so this is going to be first level, second level, third level, on every single level we are doubling all the function calls, right? So the time complexity would be the depth of these 3 to the power of 2, oh sorry, 2 to the power of depth of these 3. So 2, because it's like 2 to the power of 0 in this case, 2 to the power of 1, 2 to the power of 2, and then 2 to the power of 3. So this third level is going to be 4, then 4 times 2 is equal to 8, next level is going to be 8, then the next level after 8 is going to be 8 times 2 equals 16, and so on. So you can clearly see that this is the power of 2 progression, so it's going to be 2 to the power of n, which is actually exponential if we have, I don't know, 100 elements. So I think you already know what would be the value for 2 to the power of 32, which is integer size. It's going to be pretty big number. It's a lot of iterations. So we definitely need to optimize it. But in which way we can optimize it? So first, and the easiest thing, in Python you can put cache, but for other languages I would put maybe something else. So let's say we define our cache as an array, and for the row in range m, what we want to do is to append by default, let's initialize everything to 0, because this is our close, right? Or no, -1, because this is the cache and we want to somehow track an uninitialized value. And it's gonna be to the n, right? Right. Yes. Yes. It's gonna be n times. And now what is going on here is basically to not recalculate, let's say 8, 8. So whatever sub-tree we have for 8, 8 is gonna be computed twice, which we don't want. And in the end, there will be a lot of sub-problems recalculated every single time. So in order to omit it, the easiest technique that is possible here is to just add memoization. So whenever we calculate the sub-problem for R and C, we save this sub-problem's result to our cache, and next time we just resolve it from cache and not spawn underlying calls to the recursive function. So if cache RC is not equal to -1, which is our default value, we basically return the calculated value that it has. And also here we put it to result, and then cache RC equals to result, and then return result. So this way it should actually not give you TLA time limit exceeded anymore. Let's actually check this. Yeah, somehow it's 100%, but that should not be true. Why it's 100% and why it passed now? Because now, since our call stack is always this, oh my god, pre-order traversal, so our call stack tree is basically pre-order traversal. So we start from this, then from this, then from this, then we go here again and go right subtree, and this right subtree will be evaluated only after we calculated everything here, right? So what will happen actually is that we're gonna calculate only the unique pair of row and column, and once we calculated this, we will not evaluate it anymore. So basically, having this in mind, basically the complexity here is all possible combinations of R and C, which is actually rows times calls, which is n to the power of, oh sorry, without power, n times m. This is our complexity. But it's a bit hard to analyze in this case because, yeah, it's a recursive function, and in general, recursive functions are hard to calculate. So John answered, I don't have answer, just wanted to know your ideas why. I was referred to Microsoft, but was rejected and didn't get interview. Is it possible to send my CV in PM and ask you to check it? Yeah, for sure. So first thing that I would recommend, there is this thing called ATS. Which is, yeah, applicant tracking software. So basically, if you created your CV with using some bad template or something like that, these systems, ATS, they might just not parse it well enough, and then they will reject you without even looking into your CV. This is first thing. But since you mentioned you get referred, it means most probably recruiter took a look into your CV, but there are a bunch of reasons that might happen why they didn't contact you. So first thing that can happen is that actually the qualification is not matched for this position. Second thing, it might be a dead position. So there are cases when the recruiters are posting positions just to have like some buffer of candidates in case they really need positions, but now they don't need. Third thing, what can happen, there was hire freeze, which can just happen like that, and you stop hiring because there is hiring freeze, no budget, and that's it. And there is no problem in you or something like that. Another thing that can be possible that the position was already filled by somebody else, so they don't proceed with you. And yeah, any of these reasons can be possible. You never know which one. Yes, send your CV directly to me. I will take a look. Yeah. Good. Now let's try to convert this guy to the bottom up. So how to convert it to bottom up? So first of all, since you have this cache already set, that's good. You basically gonna copy paste your recursive function, and instead of calling your recursive sub-functions, you're gonna call your cache and resolve value from there. Since it's bottom up, it's called for a reason as a bottom up, we're gonna start from the lowest possible values and go upstairs up until we have this value calculated by using all pre-calculated values. So for example, if we're on this stage, we already know that these two are pre-calculated and we can safely go to our cache and safely resolve this value. So how it's going to be done? First of all, you should analyze how your call stack tree is working. So it starts from the highest value, and every single time it goes one less. So it starts with this 99, as is already here drawn, and it goes to the bottom. And on the bottom one, you're gonna have 0 0, then 0 1, then 1 0, and stuff like that. And you're gonna like increase it, increase it, and increase. So every single time, let's say you at some value 2 3, you should know that all the values that are below 2 and 3. So for row, it should be all the values that less than 2, and for column it should be all the values that less than 3. You should have it already pre-calculated. So in this case, first of all, you sort out the base cases. So how do you do this? So you can clearly see that when it's less than 0, it's done. Like you don't even process this guy, which can be actually a bit tricky in our case to fill this thing, but yeah, let's leave this base case. Second base case is when it's 0, so we can clearly fill this base case as this. So when it's 0 0, we return 1. Now, what we should do, we should put basically the for loop that actually traverses the opposite direction that your recursive function calls. So recursive function call traverses from the highest values to the lowest, and we're gonna traverse vice versa from the lowest to the highest. So for row in range rows, and for column in range calls. Sorry, this is gonna be n, this is gonna be m. Thanks, I will send you after the stream. Yeah, sure, send me, I will check. Now, we basically safely copy paste everything that we put here. And now for this case, if actually it's not possible, right? Yeah, it's not possible here, because we are iterating from 0 to m, so it never will be less than 0. But there will be this cache value we also resolve, and we leave only these 3 lines. And as I told you before, we are changing the calls of the sub functions with the accessing the cache. So what we are writing here is cache r-1 c plus cache r c-1, and we're setting it to the current value, which we can change like this, and we don't return anything. And in the end, since we're changing recursive function call with the cache access, we are just returning cache n-1 with the same parameters, exactly, n-1. Now, what to do with this base case? Well. One possible thing what we can do is to actually allocate +1 everywhere and start working with +1 here as well. It will be a bit hack, but this is the way how we can do it, because, and also we should initialize everything to 0, because when it's less than 0, we return 0. So what we essentially did here, let me remove this guy. We actually initialized the array of the same size, but what we also added here, we added 1 extra row in the beginning here and filled it with 0, and same happened here. everything we fill with 0, and when we start from the beginning, this guy we're gonna fill with 1 actually, and this is it. When we are here, we just resolving safely 1 plus 0 is gonna be 1, same for here and here 2, and it's going to continue. Katerina, thank you. Nice. So this will be the hack. Yeah, but now it's gonna be for 1, because in our, oh sorry, no, I didn't want to open. Yeah, anyway, because now since we initialized our DP matrix with 1 plus 1, so this is gonna be 0. We have this grid, right? This is gonna be 0, and this grid is gonna be a kind of 0 0, and our real matrix is gonna start with 1 1. So that's why I'm putting 1 1. And then yes, and m is actually going to be, so it was before n minus 1, but since matrix is plus 1, it's gonna be n minus 1 plus 1. These two cancel, is gonna be n. So let's basically try to run this example. Ah yeah, sorry, my bad. Good. What do you mean it's out of range? Ah yes, vice versa, m and n. Yes. Okay, this is something which is not expected to happen. Yeah. Yeah, because we need to start with 1 1. Not actually with 1 1 even. Let me re-evaluate. So what we put 0 everywhere here, and we put 1 here. So when should we start? Yeah, then we should start actually from this place. I fill matrix like this. Yeah, this one shouldn't work actually, because we will recalculate the value 1 here. Yes. If we start with 2, it's also not gonna work. We can actually pre-compute it a bit more, so we can do like this for column in range of columns. We can say something like this, cache. So our first our first row is gonna be 1, because we know that there is only one way to go up stack here, and also the same thing gonna happen here, right? It's gonna be the same. So basically, maybe we don't even need extended space here with this trick. So what we're gonna do is to fill it like that, and after that there is also only one way of going here, so we're gonna do exactly the same, but for the rows. Yeah, and now it's perfectly gonna work starting with 1. So we're gonna start here. Let me change the color, and we're gonna just move like this, 1 by 1. Yeah, now it should actually work. What the hell? Yes. What do you mean? What index out of range? What do you mean? Yeah, we need to change everything back. Yeah, sorry for that. Yes. Same happens here. Yeah, exactly. And now, what can I tell? That it's much easier to analyze what is going on here, because you can clearly see that basically your worst time complexity is m times n. You can clearly see that there are two for loops, and your space is also m times n, because this is how you initialize your matrix, right? Now the last follow-up that we can do here is the is the optimization, right? So the optimization usually in 2DP two-dimensional dynamic programming question is just to eliminate one dimension of the cache. So instead of two-dimensional cache array, we're gonna have only one. And how it works? Basically here, on that example, what was going on, that we marked everything here as one, and then we were moving like this. For each cell we were using this guy and this guy. Then for this guy we used this cell and this cell, and for this guy we used this cell, this cell and this cell. So what could be the observation here in this dynamic programming question? That actually once we calculated everything, we don't really care what are the values are here. So if we imagine there are a bunch of rows, right, more than 3. At this stage, let me actually do it with the red color. So at this stage we don't care about all of these values. All of these values. So whatever was calculated here, we basically don't really care. What is important for us, for particular cell, is the value calculated on previous cell and the value that calculated just previously in previous iteration, so previous column. And this is exactly what you can see here, and how it can be optimized. Instead of two-dimensional DP, you can basically use one row, and how this row can be used. Let me move back. So for some specific, we initializing it as a row again here, and stop thinking about it as a dynamic programming question. It's about basically calculating the array, like working with matrix, something like that. It will be much easier to grasp the thing. So let's say we pre-calculated our cached matrix as, cached array as this, and we are at this value, and we for sure know that this value is basically whatever we had here. No, since we are starting from this guy, we have our matrix pre-calculated like that. What we are starting with is we have this guy, which we can set beforehand, and we have this guy. And once we calculated value for this column, for this cell, we're actually pushing it back to cache, and we're moving forward. Now to calculate value to this guy, we need what? We need basically the value from the left one and value from the top one. Value from the left one is exactly the previous value in the cache, because we just set it, and value from the top one is the current value in the cache, because current value is the cache is basically previously calculated value in the cache. So what we do is just 2 plus 1, these two values, it's gonna be 3, and Yeah, we put in 3 here, and we're moving forward. So, in a nutshell, our cache will look like this. It will represent something like that. So these are calculated on the current kind of row, and these are calculated on the previous row. So basically, how it can be converted, that we are just initializing it like this. We skip all of these guys. At every single start, we are pushing these the zeros item to 1, because all of these are 1s. We know it for sure. And now what is going on? In our iteration, we just remove rows. Completely remove rows. And it should actually work. These are columns, sorry. Exactly. Exactly like that. And this way, it's still all, let me analyze complexity just here. So for time complexity, it's still all n times m, because we're iterating m's and n's inside. But from the space complexity perspective, it's of n at this point, because we have only one-dimensional cache. And this is how you basically do your dynamic programming optimization. This is, you can basically check it again. This is our steps. Create proper recursive function that solves sub-problem. Put memoization on top, so you don't recalculate the same sub-problem every single time. Then convert it to bottom-up using formal approach that we just discussed. Optimize the space. This is basically it. Let's move on. Oh, this is actually a cool question. I got very tilted once I saw it in the beginning. Yeah, and when I saw this acceptance rate, I got tilted even more. So let's solve this. I'm gonna apply exactly same thing here. So recursive function, then top down, then bottom up. Longest common subsequence. Given two strings text1 and text2, return the length of their longest common subsequence. If there is no, then return 0. Subsequence is a string of a string, is a new string generated from the original string with some characters can be non-deleted without changing the relative order of the remaining characters. Let's say ACE and ABCDE, the common subsequences, yeah. Yeah, this subsequence, because A, C, and E, we just skipped a bunch of the characters, right? And now, how do we do it? The problem here, that the first thing you might think about is some greedy approach, but greedy approach won't work here, because why? Let's say I have this thing like A, B, C, D, and this thing I have A, C, Y, D, and then CD, yeah, like this. So if we do it just greedily, so we're gonna match the character A, then we might match the character B, won't be matched at all. Or let me do like this, yeah, this will be actually a better example. We might match the first C, and then, no, it's also a bad thing. Yeah, like this. This is the example. So we matched A, then we moved on, and we matched C. No, in this case it's actually will work. Common subsequence to strings is yes. So basically, what is the problem with the how is this called? Oh my god, greedy approach. You never know whether you want to include some character or no. because why so? Because you might include character C somewhere. I actually cannot create some good example for that, so yes, so you might decide to not include character C, and then you would include this D, and then what might happen, yeah, let me put it, maybe if not including D would lead us to, if I put like this CDE, I recall how it can be done. So if I put H here, and then H, yeah, this is the example. So let's say you match the A, then you reach the C on the first substring, right? And you try to find C, you found C here, you matched C, right? And then basically you can match, you still can match D, right? What are other example? But if you don't match C in this case, you will match this C. Okay, anyway, I don't have the example just now for the case when it will not work, but basically, since every single time you have a lot of choices, so you might match the character or you might not match and maybe match it a bit later because it will be, in this case, much better for you because that way you will match more. Maybe we will find some examples in the discussions actually. Any test cases? Yes, test cases, so good. I'm not sure about these test cases, by the way. Okay, whatever. Can I find the test cases, please? Anyway. So yeah, the problem here is we never know which one to include, and this is why it's not the greedy problem in this case. You might think that you might just we actually might try. Let's maybe try to solve it greedily to show that it cannot be greedily solved by the test cases of the LeetCode. So the greedy approach would be that we just take the lesser, shorter string and try to match characters as long as we reach it. So basically, yeah, let's basically code it up very quickly just to show that why it won't work. So if length of text1 is more than length of text2, we're just gonna return the same thing, but vice versa, text2, text1. Yeah, and then what you might think of doing is index1 is going to be 0, index2, which is the longest one, also 0. And while index1 is less than length text1, what we do? If text1 index1 is equal to text2 index2, we basically just increase both. and just continue. If they are not equal, then, well, we can increase just the second one. Right? Yes, and this is also an index 2 length text 2. And then how we can, yeah, we should return in this case, this would be the length of the substring if we do it that way, but it won't work. I just cannot recall why. Yes. Sorry. Hi, sir, what is a good strategy to understand error reporting? Sorry, man, I have no idea what you're talking about. Hi, can you do my resume review? Yes, I can. Just send to me. So at first glance, it looks like working, right? The examples are passing. But if you submit, you will see now the example that it's not passing. Yeah, first. So this is what I wanted. Yeah, so we cannot just match from the first one because P might not be matched at all here, but S might not be matched just after. Just after. So yeah, it definitely cannot be solved as a greedy. So let's solve it as a dynamic programming approach. So what it will be at every, so we're gonna keep two indices basically. It's still gonna be the case, and our subfunction here, let's name it common. It's going to be index 1 and index 2, and our subfunction is going to perform the following. So the common, so if I1 equals len text 1 or I2 equals len text 2, when one of the index is out of range of the text variable, we are done for sure. So we return 0. There is 0 common subsequence, right? Hey, you need any type of video editor? Bro, I would ban you. If you don't stop this, I will ban you. Stop promoting like yourself in this scene. I mean, you already mentioned it. You don't have to mention it. Like, people are watching the chat, right? So otherwise, if none of them, so they are both in range, what we could do, we can actually check if our text1 index 1 equals to text2 index 2. In this case, we just matched the current characters, and what we should solve as a sub-problem is to, yeah, we should return actually maximum here, and initially it's going to be 0, but if we match them, our maximum is going to be 1, because the 1 is already matched, right? Maximum is equal 1 plus next one, I1 plus 1, and we're just shifting indices forward, because we just match them. Where to share my resume? Basically, ping me in the Telegram. So first of all, subscribe to Telegram channel called like this, and ping me somewhere in the comment. I will directly reach out to you. But instead of matching the character, we also might skip this character, because maybe matching this character later will be much more beneficial for us. So also, what we are stating here is we want to put maximum of whatever we already have, and common that skips one index, leaving another index the same, or vice versa, skipping the second index and leaving the first index as it is. And then we just basically return it. And we are starting an index 0, 0 in this case, because this is our first indices of the text, right? Yes, this is going to be the solution, but it's dynamic programming, so it will be exponential, and we're gonna have time limit exceeded. And the easiest way to fix it, I mean, in Python, is put some cache here, but since we are doing not only for Python, we're gonna put our cache in a bit more better way, so it's usable for other languages as well. So we are putting our cache here, and for like what would be our cache? We actually want to do all combinations of these indices. So it's gonna be length of text 1, and we are appending -1 as an initialized value, and we are appending here length of text 2. Now what we're going to do here, once we passed the base cases, we just check if this guy is already calculated. We put it, otherwise we put it a bit later. Now this thing should actually pass in the LeetCode without time limit exceeded, because now we don't recalculate the same indices again and again. We only calculate them once, and we don't spawn, in worst case, 3 subfunctions. So worst case, the time complexity without memoization, without this cache, is going to be all 3 to the power of n, where is n is maximum length of the strings, I would say, or minimum. No, it's maximum. Yes. Now, how to convert it to bottom up? Exactly same approach. So we're just leaving everything as it is. Shut up. Sir, why are there so many so that characters? Is it first in alphabet or something? Ah, you mean the submission? This guy? Or I don't. Sorry, I didn't get the question. So what basically we're going to do here is the following: how to convert this one to iterative bottom-up approach. So you can clearly see that in our function call, we are going from 0 potentially to the length of the text. So in the bottom-up, we should reverse this order completely, and we're starting from the longest one to, from the length of the text, and going to the 0, 0 indices. So our base case here is when I1 is equal to length of text and I2 is equal to length of text. So in this case, we're gonna extend our cache just by 1. So we could access it like this, for example. And now when we initializing it, we are putting 0 as our base case. You can clearly see it, right? And now after we finished our base case, let's just emulate the call stack in the sense that we now moving from bottom up. So since our leaves of our call stack is going to be length of text, we just gonna to do the same. So we are starting. Yeah, actually what else we should do in this case, so thinking about this example, we are building matrix like this. Where is it? Yes, so we are building matrix like this. So first is going to be A, B, C, D, E. And next one is going to be A, C, E. And this is our matrix basically. And now what we want to do is actually to fill this matrix beforehand. So what do I mean? What do I mean? What do I mean? Yeah, actually it should be filled. Right, I guess it should be filled. So yeah, let's emulate the call stack. So we're starting with these lengths. So I1 in range should be actually reversed. Reversed range length text 1 plus 1. And same here. I2 in reversed range length text 2 plus 1. And now the trick is in what is going on here. Yeah, actually it should not be plus 1. Yes, and we basically copy pasting whatever we have in our top down approach. Oh my god, stop this please. But with a bit modification. So this base case is already covered here by initializing the case, so we remove it. This caching we also don't care. It will be out of field. So in this case we're just gonna do this I1 I2 equals maximum that we have calculated. And here we just return cache. As I told before many times, instead of function call, we're gonna use the cache access call. So 0, 0. It's gonna be 0, 0. Good. And let's change it as well. So cache I1 plus 1, I2 plus 1. Exactly same here. Cache I1 plus 1, I2. And exactly same here. Cache I1, I2 plus 1. Great. Will it work actually? Yeah, I guess it should. Let's check it. Yes, it will. Now it's a bit faster than before because, of course, recursive function call is much slower than just iteration, blah, blah, blah. Also, it's better in terms of memory. You cannot get stack overflow and stuff. But in reality, you can clearly see that if we remove base cases and all this boilerplate, the recursive function and bottom-up approach is pretty much exactly have the same body. But instead of subsequent function call, we are using cache access. And that's it. That's how you convert to bottom-up. Now, we have exactly same problem and exactly same optimization for 2DP array. So instead of this thing for particular subsequence here or whenever it is, let's say here, we are interested only in the common subsequence lengths of this guy and this guy, because we are moving either one row plus, which is this one, or one column plus, which is this one. And we don't really care on whatever was calculated before. So exactly same optimization can be applied here, exactly same memory optimizations basically. So we stop working with cache as a two-dimensional array. Instead, we're just working with column. Then, yeah, but it will be a bit harder because you see what is here. So for each specific column, let's say like this. This is already calculated. This is the current one. We might want this guy. So let me actually put it with different color. We might want this guy, or that guy. And that guy will not be possible to memo as before. So this optimization is much harder than in the previous one. So how can we overcome this? How can we overcome this? Anyway, if we are talking about a huge DP table with like numerous rows, at some point we are interested only in 2 rows, right? In this one and that one, and this is the current one. So basically we can also keep the 2 rows. So let's name it cache 2, and this one I would leave as a cache. Yeah, so the cache here would be cache 2. Yes, and this is gonna be just cache. And after this for loop, what we are doing, we are initiating cache as a cache 2, vice versa. Cache 2 equals cache, and cache equals this guy. Oh shit. Caps lock. Yes, I guess this should be I think we don't need this top-down approach anymore. So where is it out of range? Ah, yes, we didn't. Sorry. Okay, this one is actually not working. Can we do actually optimization here? I guess at some point I did it once some time ago. Was it here? Let me check actually how it was done. Yeah, it was done via, so we have only one cache. So we don't keep 2 arrays actually. Yeah, then this is, understand, yeah, good. And previous one. How do we keep previous? Aha, okay, I got it. So basically, when we have this thing calculated, so we need this value, that value, or that value. So whenever we were on this stage and we needed same thing, this or that. For this value, this guy, we memoized it to variable called previous, and Yeah, and then we calculated value for this guy and put it here to cache, because I remind you, this is our cache line. It represents pretty much something like that. Yeah. And then I might use previous. Yeah. So makes sense. So let me actually remove this guy completely. Cache 1. Now what we need is previous. Initially it's going to be 0. This is going to go out as well. This is going to be previous, and previous is going to be cached here. Yeah, will it work? It will. Exactly. Okay, not really. Again, how was it done before? Now we don't understand why it does not work. Exactly, because this guy gonna be initialized all the time. Yes. As a 0, and this guy also as a 0. Yes, this is why it doesn't work. Yeah, so when you go to the P and this dynamic programming optimization on the like when you have bottom up and you have space n squared, then you optimize to O1. It's kind of a bit tricky because you need always to remember it's not about dynamic programming actually anymore. It's about how you work with this matrix or this array. So for this particular, I don't know, for some particular problem, subproblem, let's say here, let's say this one, you need to keep somewhere these 3 values, and they should be up to date all the way, and you should be careful when you move out to new row to be calculated, right? So that would be it. Yeah, I think we're actually done with this one, and let me think about, yeah. I promised you that we're gonna do Redis Sharding. Implement our custom one, basically. So for this, yeah, the LeetCode, I think it's done. And for this one, we're gonna check how the Redis shard is actually working. But beforehand, I would put or change. Yeah, like this. So, let's implement our custom Redis in a sense. How Redis sharding works. So what is sharding first of all, or partitioning also called, is when you split your data between different databases so it can fit and it can handle load for this particular shards. So what do I mean by that is actually when you have, let's say, let me go to my escalate row. Yeah, so let's say, yeah, we were discussing consistent hashing previous time. So whenever you have too much data that cannot fit one single instance, or which is much more actually probable that you cannot fit it by load, by request per second, so because your database just goes 100% CPU and it cannot do anything, right? In this case, you basically can split your database into 3 ones, put some kind of load balancer or whatever you want, or application gonna route it to the right database, and your database now is handling 100% divided by 3 load, which is 33. And if before hands your load and RPS would load your database only 90% CPU, which was still high, now it will be like 30 or something like that. Now, how Redis actually implements this. So whenever you, like one Redis instance is not enough, how Redis implements it. So scales horizontally with deployment topology called Redis cluster. Okay, this topic will teach you how to set up blah blah, but this is more practical one, no? So Redis uses something called hash slots. Some degree of availability during provides a way to run a Redis installation where data is shared across multiple Redis nodes. Okay. Availability during partitions. Okay. Okay, these are ports. This is actually interesting. I didn't know this. Docker containers might be exposed to this different port compared to one the program believes to be using. This is useful for animal. To make Docker compatible with a Redis cluster, you need to use Docker host network mode. Oh, okay, so it needs to be mapped to host machine ports. Okay. Okay. Okay, so here's the explanation how it works. So Redis cluster does not use consistent hashing, but a different form of sharding where every key is conceptually part of what we call a hash slot. Basically guys, I would say that this hash slot is actually virtual node on consistent hashing ring, and that's it. But let's see the implementation later. So there are 16k hash slots basically in Redis cluster, and to compute the hash slot for a given key, we simply take the CARC16 of the key modulo, this guy. So why they can afford doing this, right? Why they can use this anti-pattern, which we explained during previous session, like this anti-pattern when you do modulo of number of instances. Why is this anti-pattern? Because actually they are not introducing any new hash slots. So at maximum, at most, they can have only 16k of these hash slots. They cannot have 16k385. So with this, having this in mind, it will not be like, it will always be the static value, so therefore we can use modulo. And how actually the redistributions of the load is happening is that we are actually moving hash slots between the Redis nodes, and that's it. How often do you stream? I'm new, by the way. Your stream just appeared in my recommended. Yeah, thank you. So I'm streaming every weekend basically, and please don't forget to subscribe on Telegram, because this is how I'm announcing the stream. So yeah, you will not lose it. Yeah, here I'm software engineer at Microsoft. We are doing LeetCode and system design here. So okay, every node in Redis cluster is responsible for a subset of hash slots. So a cluster with 3 nodes where node A contains hash slots from 0 to 5k. Node B contains this range of hash slot and this range of hash slot. This makes it easy to add and remove cluster nodes. For example, if I want to add node D, I need to move some hash slots from node A, B, C to D. Similarly, I want to remove node A, and I can just move hash slots, blah, 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 blah. Good. Does not require stopping any operations. Good. However, it's kind of not true if you initiate adding one more shard in Azure, for example, which is actually a production experience I had. It will increase CPU. It might actually fail some of your operations, so better to do it during maintenance window when you don't have traffic on this Redis. Just for your information. Redis cluster supports multiple key operations, so blah 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 blah. Okay, user can force. How this exactly works? Okay, hashtags. Yeah, so this is guaranteed to be the same hash slot. Yes. Okay, master. We do not care about master replication at this point. Okay. Does not guarantee strong consistency, of course, because it's asynchronous leader-based replication, I guess. Oh, really? But it depends. If there is append only file, it will not lose, no? Asynchronous replication, okay. But it will not be a lost write, right? Once this B is back, it will. Ah, you mean that it can, yeah, another can be promoted to master. Yeah, this is actually a good case, yes. Yeah, this is actually a good catch because yeah, if we lost master, it accepts some writes, then some other node was promoted to master. Only master processes the writes. This is interesting. I still think it can be solved basically, but whatever. It's interesting. I actually never know that this is how Redis works. So yeah, what was about this thing? This is actually very important because actually it was a real case production that I had at Microsoft at some point, right? That we wanted to guarantee that we don't lose data, and this is not actually true with the Redis. I mean, it can be true for the single node Redis because actually what Redis is doing, it uses this append only file, right? So before actually to perform the write and to respond to client, Redis puts the data or the write itself to append only file, which actually something like wall, this write ahead lock in database. So once it's there, even if power is off, the shard will recover. Once it's recovered, I don't know, power is on again and all is good, it will actually recreate and recover itself from this append only file. But what is actually explained here in this consistency guarantee is that what can happen, let's say these are not shards, these are primary and replica. So this is the master, right? So let's say I'm writing here the write. It was written here. So let's say here's key 1 have value A, and here's key 1 has value A as well. My write is to set value B to key 1 as well. I'm doing it successfully to shared 1, but since replication is asynchronous, this is async, which means we send the response to client before we actually can be replicated. And we send a response to client that, okay, we put value B to key 1, but then this database basically disappeared. Powers power is off or something like that, and asynchronously it was not replicated. Then let's say timeout happened and literal action process was initiated. And in that case, let's say this shard was promoted to master, and this guy start working again, like after 1 hour or so. This guy already accepted bunch of writes, and this guy cannot accept any more writes because this is replica. So yeah, they changed the roles. Now this guy is primary, this guy is replica, and yeah, this is the problem, because this write a to the key of 1 will be permanently lost in such case, and this is actually the problem. I didn't know that. I saw what I saw that let's say if this guy has some append only file and this guy has some append only file, I saw that in this case, when this shard replica already would go live again, it will kind of sync the data back, and it will kind of repair this key to be B. Or if already some other write put it to C, it will skip this write because this write happened before. But there are a lot of problems with that, like clock skews, stuff. So yeah, I believe and I understand why Redis does not guarantee this, because Redis is usually not used as a linearizable store, right? And the store that cannot lose the writes. Yes, but you can do, I think you can do repair on read, you can do consensus in a way that repair on read, so you're writing and ensuring some of the replicas are doing synchronous replication, so write will not be lost basically, but yeah, a lot of trade-offs. Okay, now, but we are not interested in the replication, right? We're interested in sharding here. Sorry, sharding cluster. Since we want to implement our custom POC kind of, this is what we are interested in. Okay, somebody just got subscribed to Twitch. Welcome. Okay, the cluster join since bootstrap slots card. Okay. This cluster, okay. Yeah, so it sets, it tells you which slot it chose and why. Okay, this resharding process is exactly how the Redis is moving hash slots between the nodes. I'm wondering which are these slots that it is moving here and there. What about it just moved the empty slots, right? What will happen in this case? Okay, manual failover, we don't care much. Add a new node, okay. Okay, so we added empty. Which one we added actually? Okay, 7k6. What is 7k6? Or we added. Which one is which? Okay, new node is 7006. Okay, and okay, this is the hash slots it is using. And basically you can see what actually I wanted to send to you, that node in Redis is not actually serving the contiguous range of hash slots. So what do I mean by that? Let's say we have some hash slots, 0, and this is 16k, right? It doesn't work like if we have node 1, it takes this range, node 2 takes this range, and node 3 takes this range. No, it's possible that node 1 is taking care about these ranges, then node 2 is taking care about these ranges, I don't know, and node 3 is taking care about everything else, right? So they are not contiguous as in consistent hashing, I believe, because in consistent hashing, if you have your number line from 0 to 2 to the power of 32, right? If you put your nodes here, it's definitely guaranteed that this node is taking care about this slot. This node is taking care about this, range, and this node is taking care about everything else, right? So this is kind of guaranteed in consistent hashing, but it's not guaranteed in the hash slots, right? So I wonder, Redis GitHub source code. I wonder how do they do that? How the hash slots are implemented. Is there anything like hash slot or not? Or slot table. Okay, what is this guy? These are 16, I guess, keys for the hash slots, whatever. Okay, what else do we have? I want to see how it is exactly implemented in the Redis, right? Okay, this is slot stats command. This is actually already interesting. Where is the example? Okay. Okay, cluster slots, whatever. Oh shit, I didn't want to open this, but okay. So today I think we will figure out how the hash slots in Redis work, and that's it. Strike is to temporary hold slot statistics for sorting, okay. Okay, let me maybe do the following. Can I quickly actually clone it? Yeah, I actually can. So let me try to open it. Good, here's the source code of the Redis, and let's actually figure out how this beast works. I will turn off the Vim. So I'm interested in something that has slot table, whatever it is. Yeah, I don't care. What else has slot stats? Cluster slot stats. Yeah, this command, exactly. So let's see how it works. It's C++, or no, it's not plus, it's just C. So assigned slots. Start slot, end slot. Server cluster, what is server? What is server? Where server comes from? Is it in H? Somewhere here? Ah, yes, server H, okay. Okay, what is server H? Oh shit, this is pretty huge, and this is only H file, which is headers file, by the way. This is quite a long Quite a long one. Oh shit. Do you have anything related to slots? Do I have Copilot by the way here? Yeah, okay. Okay, this function might be interesting for us. Wait a bit. Get slot from command. This might be valuable for us as well. And the last one, yeah, I think this one might be interesting for us as well. Yeah, now let's go to implementation. Implementation gonna be even bigger. Yeah, 7K lines, but yeah, the end. Thank you. Let's try find this one. So first of all, how this one? Wait a bit. Where this thing comes from then? Get key slot. Where is the implementation? Can you just jump it? Oh, of course I cannot. But there should be somewhere implementation, right? It's not using cache. This is the implementation. Okay, this one. Okay, so this is how basically the slot is calculated. I think I found this function in this Redis. So slot specific dictionary for key based on keys hash slot and cluster mode is enabled. Slot specific dictionary. Okay, so this is only in cluster mode. Okay. Okay, this is optimization, whatever. Okay, so this is actually the function key hash slot. Oh, sorry, key hash slot. What is this? What is key hash slot? Where is the implementation? Here it is. Okay, yeah. Okay. So this is it. This is number of hash slots, which is correct. Hash slot given keys obtained. Latest significant 14 bits of the least significant bits. Okay, so in case we have something like this, so we just taking 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So these guys, they are going to be hash slot ID or, yeah, hash slot, good. Okay, so shit. Okay, so this is not actually what we want. Okay, this is slot, and slot is just basically the index of the slot, but when do we use this? This is the interesting key. Add internal. Okay, slot. Okay. Set value. Okay. We got slot. Okay, a bit too complicated, I would say. Okay, pops up. No. Serverage. No. Sort t hash, t list, t set, t string. Okay, okay, okay. We started where? We started, yeah, from stats. All right. Yeah. It's this guy. And we were trying to see, yeah, how, like, where are the slots? Okay, let me try a different way. Actually, cluster slots actually should be good. Okay. Start slot, end slot. Okay, 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 okay. okay. This is 16k. Nice. Yeah, back please. Yes, okay. We're iterating basically 16k of iterations. Get node by slot. Okay, we're even closer. So there is, okay, whatever. Can we, is there a bookmark? What the hell? There is no bookmark in Visual Studio Code, whatever. Okay, so I'm very close to know how they keep this mapping. Cluster legacy, so let's not look into the legacy. Let's see how it goes in the real one. In the real one, where's implementation? Am I stupid? Isn't the legacy is the only one in the source code? I mean, this is the one definition, this is not definition, this is not definition, this is not definition, this is not definition, not definition, not definition. This is definition without implementation. Basically, this is the only one. I mean, and we have slots as an array. All right. What is server? What is cluster? I don't know. Okay. Maybe we have cluster. Do we have here slots? Some array called slots. No. Who is server? Okay. I a bit forgot how the C code works. But where is this variable comes from? It's a set of different, okay. Set of definitions. Okay, where is this server comes from? Come on. Okay, let me do this one. Server equals. Okay, whatever. I still have no idea where server comes from, but whatever. So cluster size, oh sorry, cluster state. And we are particularly interested in what? It's not very convenient, let's be honest. We are interested in slots. So how slots are initialized. They are not initialized. They are not fucking initialized. Ah, no, okay, they are initialized. Yes, so cluster slots, size of server cluster slots. And what is the size of? It's interesting. Okay, again. Global struct, okay, Redis server, okay. Is it true? It is true, so okay, GPT actually knows. GPT actually knows. Good, so this is the struct. Okay, eventually we got the struct in the source code, okay. And the struct should have cluster. Yeah, this should have actually cluster. Yeah, let's use AI as much as possible. So we're gonna find this code actually, cluster state. So cluster slots. Yeah, I think we're gonna find it. Yeah, this is the cluster state and cluster slots. It is actually going to be yeah, it's exactly 16K. Good. So this is basically array of cluster nodes. Yeah, so this is not a hash map, it's basically array. Okay, now I'm wondering how is it not, how they can move them between the nodes. Okay. Assigning slots to node. Great. Okay, we're gonna find it. So it's cluster legacy, but there is no cluster C. Haha. Find me the not legacy cluster. What the hell is this? I'm sorry, but why I cannot see cluster? Yeah, I can see, and here I should find this guy. Out. Only in legacy. Okay, whatever. Let's check. So specify slot to the list of slots that node n will serve. Okay. Basically, cluster has array of slots, and slot has n, which is cluster node, and that's basically it. Okay. Did our GPT answer us the same? Yeah. Each Redis node has this cluster C. I see. So basically, how is it? Yeah. So we have Redis. This is a kind of process, right? We have array of slots. It's this 60K384, I guess. How many? $384 exactly. 384. Yes, and every single item here is the cluster state or whatever it is. Cluster node. So whenever we have some slot, which is basically index or number of slot, we go here and we check what is the node responsible for this slot. And I would say cluster node. Yes, what does it have? Yeah, okay, type dev. So it has IP and port. Exactly. That's basically it. Every node in cluster. Okay, and this, so it means that this thing is actually in every single node. You just copy paste it, and by using some gossip or whatever else protocol, Redis keeps this thing consistent in a way. Next node A and asks for key foo. Node I computes the slot. Yes. Looks up server. If node I is not responsible, it replies with mood. Yeah, it uses gossip protocol to propagate. So they do propagate via gossip. Okay, okay. Is it a real thing, by the way? Yes. Yes, yes, yes. Yeah, it updates mapping. Okay. Does it update? Okay, I don't see actually that it... Okay, good. Custom replica that does only slot. Okay, this is what I was interested in. If client sends a request to a replica slave, here's what happens. Process command server C. Okay, hash slot. We computed hash slot. Yes. Slot. Yeah, we get the cluster node. If it's not myself, we redirect client. Good. Yes, Redis mood. Mood. Okay, that is very interesting, but let's assume. I cannot find this code, by the way, but whatever. I think this is the cluster update slot config with. Okay, this function is called when we receive a master configuration via ping pong. Yeah. This is it. Yeah, so it is kind of gossip in a sense, right? Good. This is kind of understandable now. Yeah, I wanted to clarify only one thing. And this is very interesting. Добре вечер. Ано, просим. Ано, в порядку. I will turn off later. It's okay. Yeah. This one I a bit don't understand, like. Whatever. So actually they can okay, let me actually check what it means. Read or only. What does it mean? Since replica support a read-only mode which enables the behavior control by replica, okay. Will reject all write commands, so that is not possible to write a replica because of mistake. This doesn't mean it's a bit misleading, to be honest. Okay. So actually it's possible. Let me check this one. Okay, good. Okay, so who is misleading me? Read-only replicas will reject all write commands, so that it is not possible to write a replica because of mistake. This does not mean that the feature is extended to expose replicants to the internet or more generally to a network where the internet is client exists because it means what it means they can know, like, isn't it violation? Okay. Okay, writable replicas exist only for historical reasons. Using writable replicas can result in inconsistency, which is true, yes, between the master and replica. So it's not recommended to use writable replicas. Okay, yeah, true. So okay. So yeah, basically I think, I think, and how the read is served. Good, good, this is good. So get node by let's get back again to this guy. Get key slot, get key slot. Yes, good. Okay. Whatever. Where is lookup key? Okay, this is not sharding anymore. So yeah, basically the sharding, as I understood, works as the following. So yeah, we legit have the array of slots. This array is maintained on the all instances. They are using the gossip protocol to sync with each other. Yeah, and each of them have basically cluster node, and this cluster node can be kind of myself or whatever. So whenever that's true, it means this hash slot particular for this key is served by me, by this current node. Otherwise, it is not served by this node and it is moved, like redirected to another node by client, to client, I mean. Yeah, and then how the slots, and yeah, it means we can basically then reshuffle slots pretty easily. So we're just moving hash slots by some commands, update it, and see and send gossip update to all the replicas. They update the hash slots ownership, and that's it. Yeah, so they are legit not continuously mapped. I mean the hash slots. So it doesn't work like a consistent hashing in the sense that it does not, like one node is not responsible for contiguous array in a sense. So that's cool. That's cool. We kind of investigated it, researched, did a bit of reverse engineering, and this will be it, I guess. Yeah, I think we did already enough for today. Yeah, so it was me, Andrei. Thank you for being with me, and see you next stream, guys.